summarized in ordinary language. A farmer furrowing the field, a construction worker carrying bricks, an understudy reading a serious assessment, a craftsman's painting, an excellent landscape. All are supposed to be working. In physics, nonetheless, the word work covers an unmistakable and exact importance. Someone who could labor for 14 to 16 hours daily is said to have a huge endurance of energy. In physics as well, the term energy is identified with work in the sense. Yet, as said over, the term work itself is characterized significantly more definitely. The word power is utilized in regular daily existence with various shapes of significance. In karate or boxing, we discuss amazing punches. These are conveyed at incredible speed. This shade of meaning is near the significance of the word power utilized in physics. In this lesson, we will analyze the questions: how can the amount of work done by a force be measured and the energy be converted to work? For work, in the logical sense, to be done, a force must be applied and there must be motion or displacement toward the force. Formally, the work done on a framework by a constant force is characterized to be the result of the component of the force toward the motion times the separation through which the force acts. For single direction movement in one dimension, this is expressed in equation form as W is equal to the dot product of F dot T is equal to Ft cosine theta, where W is work, F is the magnitude of the force on the system, T is the magnitude of the displacement of the system, and theta is the angle between the force vector F and the displacement vector T.
For our first example, a 25 Newton block is being pushed up on a plane inclined at an angle of 30 degrees with horizontal by a 46 Newton force F applied parallel to the plane. The block moves 3 meters up the inclined plane. How much work is done on the block by gravitational force, force F, friction force, and normal force? The coefficient of kinetic friction mu sub k is 2/10. For the solution, the accompanying free body diagram shows the force acting on the block. The weight of the block W, which is 25 Newton, was resolved into components parallel and perpendicular to the inclined plane. The components of the weight parallel and perpendicular to the inclined plane are 25 Newton sine 30 and 25 Newton cos 30 respectively. Because there is no acceleration along the axis perpendicular to the inclined plane, it follows that force sub n is equal to 25 Newton cosine 30 degrees. The normal force is calculated as follows. F sub n is equal to 25 Newton cos 30 degrees, which is equal to 21 and 6500 Newton. Using the definition for kinetic friction, the frictional force is F sub k, which is equal to mu sub k times F sub n, which is equal to 2/10 times 21 and 2500 Newton, which is equal to 4 and 3300 Newton. Equation 5.1 will be used to solve for the work done on the block by each interacting forces. For gravitational force, work is equal to 25 Newton times 3 meters cosine 120 degrees, which yields to negative 37.5 joule. For the work done by applied force, work is equal to 46 Newton times 3 meters cosine 0 degrees, which yields to 138 joules. For the work done by kinetic friction force, we have work which is equal to 4 and 3300 Newton times 3 meters times cosine 180 degrees, which yields to negative 12 and 9900 joule. Lastly, for normal force, work is equal to 21 and 65 Newton times 3 meters cosine 90 degrees, which yields to 0. For our next example, a shopper pushes her 25-kilogram grocery cart by a force of 225 Newton inclined at an angle of 60 degrees with horizontal through a distance of 7.5 meters as shown in the free body diagram. Find the work done by the 225 Newton force and the friction. Assume that the coefficient of kinetic friction is 3200. First, we solve for the work done by 225 Newton. Using equation 5.1, we have work which is equal to Fd cos theta. Substituting the given values, we have 225 Newton times 7.5 Newton cosine 60 degrees, which is equal to 843 and 7500 Newton meter, or we have 843 and 7500 joule. To solve for the work done by the friction, we have first solve the weight, which is equal to mg, then we have weight is equal to 25 kilograms times 9.8 meters per second squared, which is equal to 245 Newton. And then we first resolve the 225 Newton force into its horizontal and vertical components. We have F sub x is equal to 225 Newton cosine 60 degrees, which is equal to 112 and 5/10 Newton. And for the force in y, which is equal to 225 Newton sine 60 degrees, which is equal to 194 and 8600 Newton. We now get the normal force F sub n using the sum of the vertical forces and equate it to 0. F sub n minus 245 Newton minus 194 and 8600 Newton, which is equal to 0. And that yields to 439 and 8600 Newton. Using the definition for kinetic friction, F sub k is equal to mu sub k times F sub n. We have 3200 times 439 and 86 Newton, which yields to 140 and 7600 Newton. Now for the work done by the friction, we have F sub k times the displacement cosine theta. We now have 140 and 7600 Newton times the displacement 7.5 meters cosine 180. And that yields to negative 1055 and 7/10 joule.
Energy plays a fundamental role in both regular occasions and in logical phenomena. You can no doubt name numerous forms of energy, from that provided by our foods, to the energy we use to run our vehicles, to the daylight that warms us on the seashore. You can likewise refer to the instances of what individuals consider energy that may not be scientific. For example, somebody having an energetic character. What makes it considerably more significant is that the aggregate sum of energy known to mankind is constant. Energy can change forms, yet it can show up from nothing or vanish suddenly and completely. Energy is subsequently one of a small bunch of physical quantities that we say is conserved. In this lesson, we will focus on mechanical energy, the sum of the potential and kinetic energies of a body, and conservation of mechanical energy. Potential energy, represented by an uppercase letter U, is the energy possessed by a body by virtue of its position or configuration. Gravitational potential energy is energy due to the position of an object relative to the Earth's ground. A raised object possesses gravitational potential energy. If it falls back to its original level, it can do work. Gravitational potential energy, or U sub g, is given by the formula U sub g is equal to mgh, where m is the mass of the object, g is the magnitude of the acceleration due to gravity, and h is the height where the object is located. Note that the reference point for zero gravitational potential energy is at the ground. Elastic potential energy is the energy due to configuration and is common in elastic materials such as springs. Elastic potential energy is stored in rubber bands, bowstrings, slingshots, and even clocks or watches that operate from a one-up spring. Elastic potential energy, or its symbol, U sub S, is given by U sub S is equal to 1/2 K multiplied by the quantity of delta x squared, where delta x is the elongation or compression of the spring and K is its force constant. Kinetic energy, represented by K, is the energy possessed by a body because of its motion. It is given by K is equal to 1/2 mv squared, where m is the mass and v is the speed.
For our first example, a 35-kilogram child climbs a 6 meters long slide that is inclined 30 degrees with horizontal. What is the gravitational potential energy of the child with respect to the ground when it reaches the top of the slide? To solve this problem, we are going to substitute the given values in equation 5.2, which is the definition for the gravitational potential energy, U sub g, which is equal to mass times acceleration due to gravity times the height, which is equal to 35 kilograms times 9.8 meters per second squared times 6 meters sine 30 degrees, which yields to 1029 joules. For our next example, a 25-kilogram child sits in a swing that is attached to ropes 1.6 meters long. Find the potential energy of the child relative to his lowest position when the ropes are horizontal, the vertical, and mixed with 30 degrees with horizontal. To determine the potential energy of the child relative to its lowest position when the ropes are horizontal, we have U sub G horizontal is equal to mgh, which is equal to 25 kilograms times 9.8 meters per second squared times 1 and 6/10 meter, which is equal to 392 joule. The potential energy of the child relative to the lowest position when the ropes are vertical is equal to 0 because its height is equal to 0. And the potential energy of the child relative to its lowest position when it makes 30 degrees with horizontal is equal to U sub G 30 degrees is equal to mg times h sub 2 minus h sub 1, which is equal to 25 kilograms times 9.8 meters per second squared times h sub 2, which is equal to 1.6 meters, minus h sub 1, which is equal to 1 and 6/10 sine 30 degrees, which yields to 196 joules. And next, we have Jane is initially walking at a certain speed so that her kinetic energy is 150 joules. Then the rain starts to fall and Jane runs at a rate of 4.2 meters per second. She has a mass of 50 kilograms. What is her initial speed before the rain starts? Find the change in Jane's kinetic energy when she starts running. To solve for Jane's initial speed before the rain starts, we have k sub 1 is equal to 1 half mv sub 0 squared. Manipulating the equation, we obtain v sub 0 is equal to the square root of 2k sub 1 over m. Substituting the given values, we have v sub 0 is equal to square root of 2 times 150 joule over 50 kilograms, which is equal to 2 and 4500 meters per second. Then, to solve for the change in Jane's kinetic energy when she starts running, we have k sub f, which is equal to k sub 2, where k sub 2 is equal to 1 half mv squared. We have 1 half times 50 kilograms times 4.2 meters per second squared, which yields to 441 joules. Then the change in k is equal to k sub 2 minus k sub 1, where k sub 1 is the obtained value from the previous questions. So substituting, we have 441 joules minus 150 joules yields to 291 joules.
Thank you very much for watching. We hope that you learned. See you on our next topic. Bye!